Hello everyone, let's solve a numerical on settlement. So this is the question. A raft foundation of 10 meter by 15 meter is there. The depth of footing is given, net intensity of loading is given, water table depth is also given. The soil profile is given. It is a layered soil. Layer 1 is up to 7 meter, layer 2 from 7 meter to 19 meter. The related soil properties such as Poisson's ratio, modulus of elasticity, pore pressure coefficient, unit weight of the soil, undrained cohesion, etc. are given. Now, coming to the solution part, we know this already that total settlement will be having two components. One is immediate settlement and one is consolidation settlement. Then influence zone, this is also we know that influence zone will be 2 times the width of the footing. In this case, it is seen that data is available for 16.5 meter only from the base of the footing. Then we have a bedrock. So it is assumed that deformation will occur only in the clay portion, and the influence zone will be up to the level of the bedrock, and which will be less than 2 times of width of the footing. This is the formula for finding out immediate settlement. We can find this formula in IS code 8009 part 1 1976. In this case, modulus of elasticity is different for layer 1 and layer 2. So we have to use the weighted average in the formula. Thickness of layer 1 within the influence zone is 4.5 meter and layer 2 is 12 meter. Using these values, we find out what is the weighted average of modulus of elasticity. Then going back to the formula, net intensity of loading, width of the footing, Poisson's ratio, all are given in the question. So using them and influence factor, it is taken from table 2 of IS 8009 part 1 1976. This value is corresponding to the center of flexible footing. And later we have to apply a rigidity correction because this is a raft footing which is considered as a rigid footing. This is the table in IS code from where influence factor has been taken. L by B ratio in our case is 1.5. Corresponding to that, 1.36 is the value in the center. So this 1.36 is to be used in the formula. Now we have to apply two corrections, depth correction and rigidity correction. This is the figure number 12 in IS 8009 part 1 1976, from where depth correction factor is to be taken. We have two parts here. Upper part is when depth of the footing is smaller, lower part when depth of the footing is higher. Now, this is the portion to look for our case. The depth factor is given corresponding to L by B ratio and the factor D divided by root over L into B. In our case, L by B ratio is 1.5 and the factor D divided by root over L into B will be 2.5 divided by root over 15 into 10, which comes out to be 0.2. So corresponding to 0.2 and for the L by B ratio 1.5, the depth factor comes out to be around 0.95. Now this is the depth factor which we have to use in the settlement formula. Now applying the depth correction and rigidity correction, we find the corrected immediate settlement. Now this is the formula to find out consolidation settlement. I hope we already know the formula, but in this case, since it is a layered soil, we have to do summation of the two layers. We have to determine the initial effective overburden pressure and increase in effective overburden pressure in the middle of layer 1 and layer 2. So let's say that A is a point in the middle of layer 1 and B is a point in the middle of layer 2. If this is the loading intensity at the base of the footing, this is how it is assumed to be distributed in the ratio of 2 vertical is to 1 horizontal. These are the calculations for initial effective overburden pressure and increase in effective overburden pressure. For layer 1 at the middle, point A, the initial effective overburden pressure is 2.5 meter multiplied by 18 kN per meter cube. This is for the portion above the base of the footing, plus 2.25 meter multiplied by 18 minus 10 kN per meter cube. This is for the portion below the base of the footing, 2.8. The thickness of the layer 1 is 4.5 meter, so half is 2.25 meter, and water table is at the base of the footing, so we have to consider the submerged unit weight. Doing this, we find out the value to be 63 kilonewton per meter square. Now, what is the increase in effective overburden pressure? 50 kilonewton per meter square is the net intensity of load acting at the base of the footing, multiplied by the size of the footing. So this is the load acting at the base of the footing. Now it is dispersed. We have to find out the intensity at the level of point A, at the middle of layer 1. Now we are coming down 2.25 meter from the base of the footing. So in the horizontal direction, in one side we will go 2.25 divided by 2, and on the other side we will go 2.25 divided by 2. So net we will go 2.25 meter. So the breadth will be 10 plus 2.25 meter, and the length will be 15 plus 2.25 meter. So doing so, we find out what is the increase in effective overburden pressure. Similarly, for point B at layer 2, we do the calculations and we find out what is the initial effective overburden pressure and increase in effective overburden pressure. Now coming back to the formula, putting the values of layer 1 and layer 2 and adding, we find out what is the consolidation settlement. Here we have to apply 3 corrections. Depth correction 0.95 is same as previous. Rigidity correction 0.8, it is always 0.8. Then pore water correction. Now this correction we have to take from figure 10 of IS 8009 part 1 1976. This is figure 10 of IS 8009 part 1 1976. From here we will have to select the correction factor corresponding to pore pressure coefficient. The values on the curves are HT divided by B. HT is the thickness of the clay layer, which is in our case 16.5 meter. B is the weight of the footing, which is in our case 10 meter. So HT by B in our case is equal to 16.5 meter divided by 10 meter is equal to 1.65. Then pore pressure coefficient is given as 0.6. Then we have to select values corresponding to strip footing. So we see that our value will be slightly below the curve whose value is equal to 1. So we see that the correction factor is almost 0.8. Actually, we should do a linear interpolation between the values of strip footing and square footing, but we can approximately select the values for a strip footing. So the correction factor in our case will be around 0.8 for a pore pressure coefficient of 0.6 and HT by B equal to 1.65. Then if there are no pore pressure data available, there are some recommended values just above this figure in the IS code that can be used. Then we apply the depth correction, rigidity correction, and pore water correction to the consolidation settlement. We find out the corrected consolidation settlement. And finally, we add the immediate settlement and the consolidation settlement to get the total settlement. Thank you.